What's up guys? I got another tutorial for you. I'm super excited about this one. We're going to be using animation nodes to produce a Chladni plate and then do some simulations with it. This tutorial is going to be in 3 parts, so I'm going to show you like a very simplified way of doing this just to get you set up. If you're a little unsure about the math and everything, that should set your mind at ease. And then we're going to move into doing, I'll probably show you the way I faked it first. It's actually a little bit more straightforward. And then I'll show you the actual particle simulation I did to produce like the most realistic version of this. So let's go ahead and get started. Alright guys, sorry for the long delay. It's very good to be back. Today I'm going to show you how to produce this kind of geometry using animation nodes. My goal in doing this is not to show you how to do exactly what I did, but to provide you with a technique that you can use to produce all kinds of similar related animations, cool geometry, cool looking stuff. So we're eventually going to get to this point, and then I'll kind of give you some tips on how you can use this similar node, or this node tree and node tree similar to it, to produce all kinds of stuff. So let's go ahead and load a startup file. We're going to keep our default cube this time. I'm going to rename it particle just so I don't get lost. Then I'm going to open up a new window and switch it to the node tree view. So this is animation nodes. I already have it installed. If you don't already have it installed, what are you doing? I'm going to create a new node tree. Let me just, since this is the first time I have used animation nodes, let me show you something that's kind of important to keep in mind if you're working on a laptop, less powerful desktop, or if you're trying to record a tutorial at the same time. You'll probably want to keep in mind that by default animation nodes executes the node tree constantly, and you'll have a readout of how long it's taking to execute the whole node tree in this corner. If you look up some other tutorials, there is a way to make this change or have the node tree execute based on things that you're doing in this window. By default, it'll only execute, not by default, but if you have property changed enabled here, it'll execute when you change things only in the node tree in this view, not up here. But there's ways to get around that. I'm working with, not the most powerful machine on earth, but purpose-built desktop. Very proud of it. So I'm going to leave it on always execute unless I run into problems. If you start trying to do too much with too much geometry, you may need to slow that down or have it execute at a higher time interval. So first thing we need to do is get this cube into animation nodes so we can do some stuff with it. So I'm just going to add a object node and select our particle. You don't really have to do this. You'll see later most of the nodes have a way to select what object they're operating on within the node itself. I just like to do this because it keeps things organized. So first of all, let's just see if you do a transforms output and tell it which object you're trying to operate on, and enable, this is, let me zoom in a little bit for you guys, this is translation, rotation, and scale. If you enable X, Y, and Z translation adjustments, basically, you can now move that object around. So first thing I want to show you how to do, I want to create a bunch of these in a grid. So one of the easiest ways to do that is to just create a grid here in object mode. I'm going to take that grid, go into edit mode, and scale it up just so they're further apart. So we are only going to use this grid as a list of vertices. We want the locations of each of these points. Tab back into object mode for no real reason. Let's get this grid into animation nodes so we can do some stuff with it, and it is just still an object. And we'll select our grid. Now, all I really want from this is a list of vertices. So I'm going to show you how to separate that object into a list of vectors that are its points. If you do, mesh, separate, This will give us vertex locations, but first we need to convert this object into its mesh data. So I'm going to do mesh data from object, and tell it that we want to do this object. So now we have mesh data coming out of here. We input that, and we have a list of vertex locations, the edge indices, polygons indices. I haven't worked with these two very much. This is all we're worried about. You can see from the color of the output that it is vertices. But if you don't believe me, this is a good thing to know anyways, you can open up a viewer, and this is just for debugging, figuring out what you're doing. This will take pretty much anything. I think that's what red means. And it'll tell you what the output of that node is. So in this case, it is a list of 100 vectors, 3-dimensioned vectors at each of the vertex locations of this grid. So it's one data point for each of these actual points. So we want to put one of our cubes at each of those points. So we're going to do something called the instancer. Since we only have one cube right now, that's not going to help us very much. We need a bunch of them. In fact, we need as many cubes as are vertices in this list. So let me show you how to do that. If you go into the list section and get length, that is just going to output a integer that is how many items are in this list. So it should be 100. Bam. We need 100 of that object. Now they're all stacked on top of each other. We could do this. They're still stacked on top of each other. And you see two of them. This is the original cube, which I'll go ahead and hide. That's just kind of something that arises when you use the instancer. The original object that you're instancing remains. So I'm going to hide that just for fun. And right now we have 100 of these objects. I think you can see that if you open, yeah, we have 100 of these objects all being given the same X, Y, and Z location. So still not extraordinarily helpful. Now you might think, oh, we could input a list of X, Y, and Z locations into this like that. Oh, so we can. Interesting. Okay, but we still don't have a whole lot of control over those things. Man, I'm wondering if I can do this whole thing without loops. We're going to use loops anyways, because you're going to need to use them at some point. Let me show you how to set that up, and then I'll explain why we're setting it up. So if you do subprogram, create a loop. So this creates the loop. We're going to call it location. And then you invoke that subprogram. This lets you use it in this node tree and do operations down within the loop. It'll make more sense as we go, hopefully. So I'm going to create some inputs for this loop down here. We need a new iterator that is a vector list. And now we can input this list of vectors into here. And if you use our, where did our viewer go? Let's get a new viewer. You'll see that within the loop, we only are addressing one of those vertices at a time. And it's going to perform an operation on each one of them individually. So a list comes in, and then a list item comes out, and it performs a loop for each of those iterators, meaning the input was an iterator, not a parameter. A parameter would just be a constant that is used for every instance of the loop, every iteration of the loop. An iterator is saying separate this list into a single item, perform the operation on that item only, and then move on to the next one. So we want to take our cubes and put them at each of these locations. So let's do a new iterator that is a object list. Now, each of these 100 items, this list of objects, is now being operated one at a time, and we're going to take each of those and place it at each of those locations. Why doesn't that work for me? Oh, because we lost our, somewhere along the line, we lost our list length. So again, the list length is how many instances we want. In this case, it's 100, but that could change down the line if you wanted to, oh, I don't know, delete one of those vertices. Now when you tab out of edit mode, it's not there anymore. Let's undo that. But now we have a cube at each of these vertex locations. Excellent. Not very interesting so far. Let's do something else with the information that we already have. I want to show you that you can separate this vector into 3 separate floats and then combine it again. And if you just take these 3 values straight across, these together are doing nothing. They're separating the vector and then combining it, so we should get exactly the same result. But if you say set the z location to also be the x location, now every single one of those cubes, its z location is the same as its x location. You could also do something interesting in between the separate and combine vectors. Like say do the absolute value of x. So now all the z values will be positive and you get this V shape. You could also do something even more interesting and have the z location be the sine of the x location. So we don't really have enough resolution to see very well what's going on, but if you know what a sine wave looks like, you can see that it's starting to approximate one. And basically this whole technique is just based on performing math on the vector of the location. So let's add another math node and say multiply x by 0.5 before it gets to the sine. And as we adjust this, you're essentially changing the wavelength of our approximated wave. So at 0.25, it is 4 times the original wavelength. And this is in radians, so if this is at 1, it's every 2 pi, so 6.28 x units, Blender units, represents 1 full cycle of the wave. And as you decrease this, you're stretching the wave out. As you increase it, you're making it smaller and smaller until the, is that what we're doing? Doesn't look like that's what we're doing. Probably just the fact that we only have 10 sample points. It's going to make it do some weird like aliasing things. But we can do even more math. Let's say we want to do a wave in the y direction also. Let's duplicate this part, have y as the input, and then we'll superimpose the 2 on top of each other, which just means that we add them together. And have that, come on, we'll have that be our z location. Now, in both x and y, we have a wave, and those are superimposed on top of each other. So if I do, just to make it real easy to see, 0.5 and 0.25 in our x direction, we have one wave, in our y direction, we have another wave. And that, believe it or not, is pretty much the entire technique. It's just a factor. It's just a matter of doing more and more complicated math with the x and y location to produce your z location. One of the other things I did was, instead of producing a cube at each of these points, I just took the original grid and I adjusted those grid points and then output it so it was a single smooth surface. And then I did like a subdivision surface so it was a little bit smoother, it didn't need as many data points. And then I did a particle simulation, an actual physical simulation of objects dropping onto that plane that is warping as time goes on. Oh, I should show you how to do that really quick. So if you want this to actually move without you sitting here and doing this, then you need to get time involved. So if you do, it's under animation, I believe, animation time info, this lets you input the current frame. And you'll need to go over here. You don't have to do this, but it helps me if I do frame rate, enable that as an output over here in your properties panel. I just do, so I can think about things in seconds, I just divide the current frame by the frame rate. So if you have 60 frames per second, at the 60th frame, this will output 1 second. It's measured in seconds now instead of frames. Just doing frames by itself might be more useful for whatever you're doing. I just like to think about things in actual, physical properties that I can think about. So this is our current frame. Let's just do one more math node. We'll actually need 2 of these for X and Y. But if you take the result of this multiplication and add the current time to it, this will oscillate in the X direction. And you can adjust the speed of the oscillation by multiplying this value, doing all kinds of stuff. You can make it move further up and down by multiplying the final result. So instead of oscillating between -1 and +1, it'll oscillate between whatever you multiply it by. You could do an absolute value here and they'll bounce off the plane. You can do all kinds of stuff. The important thing is to know what you're doing with the math to get there. Okay, one more thing I want to show you. One more thing I want to show you. It is just using fancy math, but I think it's a useful thing to know. Who here can tell me? Raise your hand if you know Pythagorean's theorem. We're going to, one too many. We're going to use the Pythagorean theorem to perform some math on these cubes based on how far they are from the center rather than just their X and Y location. So let's fire up where is it expression? Yeah, an expression. We're going to do a Python expression just because this is going to get a little messy. And this is another really good thing to know how to do. This is, instead of using like a dozen math nodes, you can just use one expression and do all the math in there and then output whatever you need. So I'm going to add some floats as inputs. And this is all happening within the loop. So we don't have a list of floats coming out of here, we just have one float per object. The operation is being performed on each individually again. So X and Y, they're already named that. Use your X and Y as inputs. And then we're going to do, okay, what is it? We want X squared plus Y squared, and we want the square root of that. Now our result is essentially the distance of each of these points from the center. Boom. We got that going on. And now you do the same thing to make it oscillate. We just do another math. And you could do this within the expression. This does everything that the math nodes do. In fact, this is probably, it is for certain just Python behind the scenes. But sometimes separating things out will make it easier to look at, make it easier to go back and find what you were trying to do if you ever return to a project. So just take the sign of that. boom, and now let's make it oscillate in time. So again, take a math and add the current time in seconds. And it oscillates. And again, if you just wanted to make that faster, one more math node. This is now making it go twice as fast. And keep in mind when you're watching these animations in real time, if your animation node's tree is taking too long to execute, you won't be able to see these in real time. I think this turns red. This one turns red if it's not playing back in real time. So, yeah, it's oscillating in both directions and it's based on the center. Well, it's based on 0, 0, which happens to be our center. If you wanted to use another, let's just do that. Let's add a empty. I'll just do a plain axis. I'm going to call it center, even though it will not eventually be our center. And let's do blah, blah, blah. Get this object into animation nodes. So that's our center. And we'll base, yeah, so we want the distance from that empty's location rather than just 0, 0. So there is kind of, in this expression, there is an implied distance from in here, so it's actually not x, it's x minus, what's the best, let's do a. And this is going to break it because we don't actually have these variables in here, but y minus b, and it'll break as soon as yep. Add a new float, call it a, and another new float, call it b, and we're also going to need those to be in our loop, so we add a new parameter, not an iterator. We don't want to iterate for every, there's only one of them, but we don't want to iterate for every single one of those. So we just have a single vector, and this is center location. And we do the same thing. I wonder if we can just do, yeah, transforms input for this. Its current location, input that as a single vector into our loop. Now we have that. We separate that vector. Oh, just duplicate that. Put it somewhere where it's not going to insert itself into the middle of the wires. And our X and Y location of our center is now the center of all this oscillation. Again, kind of hard to see with only 10 points. It might be, no. You see what I'm talking about though. So fun stuff to be had there for sure. But again, as long as you realize what the math is doing and you understand it, you can do a lot of different things with this technique. I think I'm going to go ahead and end it there. I'll try to post screenshots of this node tree, maybe clean it up a little bit, and the node trees that I used for all the different iterations of this project. Again, to do the actual simulation one, it was just a normal particle system with a hard body physics enabled, falling onto a plate that it was one continuous surface that had its vertex locations modified by a tree that looked very much like this. So hope you enjoyed that. Hope you learned something. I'll see you next time. Hopefully it won't be so long before the next one.